So last time in the lesson on writing quadratic equations, we did briefly talk about the shape of a quadratic graph. So particularly, a quadratic function has an x squared term being the highest exponent. That is what really makes something be a quadratic. If it doesn't have the x squared term, it's not a quadratic. So we have an example of a y equals x squared graph over here on the right hand side of the screen. And this is what the basic x squared graph is going to look like. We're going to get into details how you get those points on this graph. I'll give you a hint. It's very similar to what we did with linear equations when we made a table of values. Our table of values is just going to be a little bit more specific. What I also want you to know is how things like a 2 out in front, a -3 on the inside of the parentheses squared, and a 4 added on the outside affect the function as well, because this works for every function that you ever learn in mathematics. So let's think about logically what would happen mathematically with those numbers. The 2 would multiply the whole thing right here by 2. So after we square it, and we get a funky looking number maybe, we multiply it by 2, so it's going to be twice as big. So think about what that would do to the y value. It would take that y value and it would multiply it by 2, so it would kind of stretch it up from here up to here. Notice the word that I used there. It's going to stretch it up. It's not going to move it up to. It's going to stretch it because it's going to multiply it by 2. This point up here at 4 would actually end up being at 8 because it would be twice as big. What would the -3 do? Well, the -3 on the inside is going to take this x value, say 0, and it's going to subtract 3 from it. So what's going to happen is if I plug in 0 for x, the graph is going to act like it used to over here at 3, so it'd be way up here somewhere. It's actually going to scoot this way to 0. And I know that's kind of weird because you see -3 and you think, hey, that means it's probably going to scoot to the left 3 spaces. But that's not actually what happens when you subtract 3 from 0. Your graph acts like it used to at -3 when you plug in 0. So essentially it's sliding this graph to the right hand side over here. Now let's take a look at the 4. The 4 is adding 4 to everything that you've just done. So after you've moved it, after you've stretched that graph up, the 4 is adding 4 to the final answer. So think about what that would do. After I've moved this point this way and stretched it way up there, then it's going to go up 4 still. So this one is going to move it up. So what happens is when I have this format, by the way, you should recognize that format. It is the vertex form of a quadratic. This number right here will stretch the graph up and down, and sometimes it'll compress the graph if it's a fraction. This guy right here will move the graph left and right, but it always moves the opposite. That should sound familiar to you. And this guy right here moves the graph up and down. It always moves it the same. Remember last time on the writing equations, we talked about how the vertex form is called vertex form because if you take the opposite of this number and the same as this number that's added or subtracted. So in other words, the opposite of -3 and the same as 4, that is going to be the vertex 3, 4 for your new parabola. Guys, what that means is look at this graph. It's moved it to the right 3 and up 4. And then the 2 is going to make this thing get a little bit skinnier than the original graph. So it's going to stretch it up taller by multiplying by 2. Those 3 numbers, if you can understand that concept, will help you with every function you ever learn, especially when you get into Algebra 2. I don't want to bog down too much with that, But what we're going to look at today also is how the different forms of graphing a quadratic require you to do different things, specifically to find that really important point called the vertex. But then everything else about graphing it is the same way of making a table of values like you did with the first linear equation graphs. So what we're going to look at today, like I said, is taking a look at the graphs of a quadratic. Remember, there was 3 forms that we talked about. We talked about standard form. That was that ax squared plus bx plus c that we talked about. Then we talked about vertex form, and we just reviewed vertex form a little bit just a second ago. Vertex form is that form where you have y equals the a times the x minus h squared plus k. Remember, the a, the h, and the k are just numbers, just like the a and the b and the c. And then we had intercept form. Now, intercept form, interestingly, is going to be one of those that we come back to even in the next lesson when we're talking about solving a quadratic. So intercept form is pretty important for us, like vertex form. It tells us a good bit of information about the graph. So these graphs, like we said last time in class, also important thing to remember is they make a U-shaped graph that's called a parabola. Remember, this U-shaped graph, when we talk about a parabola, has a very, very important point right here and right here, because these graphs can open up or they can open down depending upon the leading coefficient, a. So in those standard form, vertex form, and intercept form, if this leading number is a positive, it's going to open up. If it's a negative, it's going to open down. And we also just learned in the vertex form, it's going to stretch it. It would do the same thing in intercept form and the same thing in standard form. Anytime you multiply a number times that x squared portion, it is going to make it stretch or compress if it was a fraction. So that number out in front, not only is it going to tell me which way it opens, it's going to tell me how skinny or how fat my parabola is. Sorry, I probably shouldn't use the word fat, right? It's a pleasantly plump parabola. Sorry, guys, math teacher joke. All right. Also, not only does the leading coefficient tell me if it opens up or if it opens down, like I said, it tells me how it stretches, but it also tells me that that vertex is going to be either a minimum point at the bottom or a maximum point at the top. And that has some great carryover for us into word problems when we apply this to more real-life situations. So that vertex is a critical point. The other thing that's critical about these is that they are symmetric. Anytime you have one of these parabolic shapes, not only do you have this vertex here, but you have these points on either side that are perfectly symmetric on either side. Whether it's a graph that's opening down, or if you had this guy right here, a graph that's opening up. You have these symmetric points. That's important because that tells me a lot about when I start graphing these. There's going to be a very specific pattern when I'm talking about a table of values. Not a linear pattern, though. Notice this graph is going down quickly, but then a little bit slower, and then it changes directions, and now all of a sudden it's going up. The key thing with a parabola is that the slope is constantly changing. And in fact, if you get into calculus later on, you're going to talk about something called the instantaneous rate of change. How quickly the graph is changing here, all the way around it, and it changes each time you're changing direction or getting steeper or less steep. But the important part to understand is that you're going to still see a pattern. A function does follow a specific pattern, and the pattern that it follows tells me typically what kind of function it is. And so we're going to see this little mirror image where the numbers repeat on the other side in our table of values. It's not going to be like linear, which makes a straight line and it has a constant pattern. It's going to be changing, but it's going to be a pattern. So it's going to make this little U-shaped graph called a parabola. So what we're going to do is we're going to take our 3 different forms, our standard form, our vertex form, and our intercept form, And we're going to use those forms to find one specific point first, the vertex, and then we can find the pattern around it, or the U-shape that's on either side. Because if I know my vertex is here, then I know my U-shape is either going to be coming down to this point and back up, or it's going to be coming up to that point and back down. And I know those are not real pretty graphs there. So we're going to make sure that we can find the vertex for standard form, the vertex for vertex form, and the vertex for intercept form. So I do have some notes about standard form, but I am not going to leave them on the screen for a really long time. I want you just to be able to go through, and if you want to pause the video here, you can copy some stuff down. But a lot of this stuff we've already been talking about. Like I said, the graph of that standard form is a parabola. If the a value is positive, it opens up. If the a value is negative, it opens down. The key part about this particular screen is right here. The vertex. This is that key point on that parabolic shape. The vertex has an x-coordinate of negative b over 2a. Now you might be thinking, what in the world are you talking about? There's some b's and a's. I don't get it. What are you supposed to do? If you know what the b is in the original equation and the a is, remember those are just numbers in these real problems here. If I know what those numbers are, I can take the opposite of the b, or negative b, and 2 times a and divide it, and that gives me the x value of my vertex. And that's going to be important, because if I know the x value of a vertex, just like if I knew the numbers that I'm plugging in to a linear function, then I can plug this number in to find the y value. And that's what this next note says. It says the y coordinate is what you get for y when you plug in to the function negative b over 2a. And I know that looks ugly, guys, but what it really means is if I take this and I plug it into the function for x, I can get my y value. The axis of symmetry is also going to be straight down through the middle of that point, negative b over 2a. And then I gave you a little extra little side note here. The intercept, the y-intercept, is whatever this little c value is here, because when you plug in 0 for x to get your y-intercept like we did with linear equations, you plug in 0 for x, it gives me c. That's going to be my y-intercept. So I know that's a blitz of information about this quadratic function, but I didn't want to spend too much time on the notes. I want us to actually do it. I want us to actually look at a quadratic. So my first example that I'm going to do with you is y equals x squared minus 2x minus 3. So in this process, our first goal is going to be, can we find the vertex? Can we find the vertex? Now specifically, I'm going to erase that here. Specifically on a standard form, we are going to find the x value of the vertex. And I'm going to put that and point that out because I want you to know that it's only finding the x. We would have to plug it in to find y. So if I want to find the x value of the vertex, what I did was I gave you a little formula. I said if you take the opposite of whatever the b value is in the problem and divide it by 2 times a. In other words, the x value is the opposite of whatever is right here beside the x. It's the linear term that we called it. And then whatever is here is the coefficient in the front of x squared, the a. If we take that negative 2 and plug it here, and that positive 1 and plug it there, we can find the x value of the vertex by doing just a little bit of math here. A negative times a negative makes positive 2 on the top. 2 times 1 on the bottom is 2. So what is 2 divided by 2? That is 1. That means on my graph over here, you don't have to draw this, but that means my graph has a center or axis of symmetry at 1. I don't know where it is yet, but I just do know that my U shape is going to come to this line and then come back up, or it could come back down. Now I can tell, because this a value is 1, it's going to open up. I just don't know where it's at yet. So this is how you find where the graph actually is. If you know where the vertex value is, and you know that these shapes make a U shape, you know that the vertex is in the middle of that U shape, and you want to find the rest of both sides of the U shape. Yes, I'm kind of exaggerating here a little bit to hopefully keep your attention. What you do is you are going to make a table of values, meaning you're going to do exactly what we did with linear functions, but instead of taking and just doing some random numbers in here, I am going to make sure that the vertex, because it's in the middle of my U shape, the graph is the same on both sides of the U shape. I want to take this guy and I want to put him in the middle of my table. Let me repeat that again and show you again. I know that this x value of this vertex is in the middle of my graph. I know that the rest of my graph is on either side of this. So I take this 1 right here and I'm going to plug it in the middle of my table. Remember, this is the whole concept of plugging inputs into a function to get outputs. Now, the next thing I want to do is I want to find some stuff to the left of 1 and to the right of 1. Remember, this is my x value, so it's this way and this way. So stuff that's to the left of 1 and stuff that's to the right of 1. Those are the numbers that I want to plug in at my table. But it's actually very easy. All I have to do is count, meaning I count up to 2 and 3. 1, 2, 3. I count down from 1 down to 0, down to -1. Yeah, I know negatives are there, but you take those numbers with the vertex in the middle because it's the middle point on the graph, and you substitute those numbers in for x, and you get your y values. Just like we did with linear equations, the only difference with linear equations is I could use the same numbers over and over again. With a quadratic, that vertex may not always be in the same spot. So what I have to be able to do is move that vertex around and change what I put in for x's. So what I'm going to do is I'm going to plug in -1 for x. Plug in -1 for x and do the math. Plug in 0 for x. Plug in 0 for x and do the math. Plug in 1 for x. Plug in 1 for x, and then plug in 2. Now, I know I'm kind of just over-exaggerating here, this middle column. I know some of you are thinking, Mr. Harrison, I'm just going to use the calculator. I'm not even going to write the middle column. That's fine, as long as you know what you're actually plugging into. And notice that I put parentheses around the x when I plugged it in, because I want to tell the calculator to square that. So what we're going to do now is we're going to look at what that looks like when we go to Desmos. Okay, so if I go to Desmos, and I'm going to type this in. I'm going to take and I'm going to make my parentheses here. I'm going to plug in -1, and then I'm going to square it. Now, if you don't know how to find the squared thing, it's down here on the calculator, or the little keyboard right here. Or you can actually also hit the little, it looks like a little rooftop looking key above 6. That's going to be the caret key, they call it. And then I'm going to have -2 times -1. And then I'm going to have +3. Let me make sure I did that right. -3. I knew I messed it up. If I do that, it tells me the value right here is 0. So my y value is 0. -1, 0. -1, 0 is my first value right here. So then what I'm going to do is I'm just going to keep on going down through these points. Now the good news about Desmos is when I change this to 0, notice nothing else about the function changes. I didn't get a new function all of a sudden. All I have to do on Desmos is come over here to my -1, erase it, and put 0. Come over here to this -1, erase it, and put 0. Oh my goodness. And then it gives me my next value, my y value of -3. So my y value for the next one is -3. So that is 0, -3. So I'm starting to see my shape coming down towards my vertex. Notice, again, this graph is opening up because the positive a value, that means my vertex is going to be a minimum value, or a bottom. So then I go back to Desmos again, and I change this from a 0 to a 1. From a 0 to a 1. And I get -4. Now, what did we just talk about with the vertex? We said that point, the vertex, is going to be the lowest point on the graph. So it goes down here to -4, 1, -4. Notice that's on my axis of symmetry. What's going to happen on the other side? Here's the cool thing about parabolas. It does have a pattern. It's not like linear, but it does have a pattern. You know that if you plug in this next one here, you're going to get 4 minus 4, which is 0, minus 3 is another -3. You're going to get 3 squared is 9. 2 times 3 is 6, so 9 minus 6 is 3. 3 minus 3 is 0. You're going to get the point 2, -3, and the point 3, 0. Notice it's just a mirror image, and it does this little flip-flop in the table, because what it's doing is it's going down to -4, and then it's coming back up on the other side. So when you're going through this graph, it's going to have that shape every time. The only time you're not going to see those pretty little numbers and pretty little mirror image is if your x value of your vertex in the middle is kind of ugly, meaning it's an ugly fraction or something. But you can still plug in numbers on the other sides that are not ugly fractions if you want to. I'll show you an example of that here in just a little bit. So now, for this graph, we just connect our dots here. Remember that every point on this line, or in this case, a curve, every point on this curve is a solution to this equation. If you plug in -1 here, -1 here, you're going to get 0 over here. If you plug in 1 and -4, plug in 1 here, and -4, it's going to be everything over here equal to -4. These points are solutions just like they are with linear equations. So, now we have our graph of a parabola. Now, let's take a look at a couple of other examples. I'm not going to go through every single step of this every time because you should, at this point in Algebra 1, be able to make a table of values. That is something that is an important skill. We'll practice a little bit, but I'm not going to go through in huge detail. If you want to, you can try to go ahead and practice the problem and pause it first before I go through it if you want to try it. So this is the standard form, and I want to find the x value of the vertex first. So just like I did before, I'm going to find the x value of the vertex by doing that little formula, -b over 2a. So I do negative, and then I plug in -1 because that's what this is. 2 times a, I have 2 times -2. That's going to give me 1 over -4, or in other words, that's -1/4 as a fraction. Now guys, as I go through these examples, I'm going through pretty quickly, but you can always use your calculator like I've told you before to help you. So remember, let's talk about this again. The x value of the vertex is the middle point. It's the middle value. And so what I do is I literally take and put this number in the middle of my table, because now I want to get some of the left side of this and some of the right side of this. The problem is 1/4 is ugly. Ugly. But that doesn't mean my other values for x are going to be ugly. I can choose easier numbers to plug in than fractions for the other numbers. What that does mean, though, is my pretty little pattern that I saw over here, I'm not going to see it in the table, but my graph will still be a parabola. So what are some numbers that are bigger than -1/4? That would be things like 0. Even though -1/4 is like right here, 0 is bigger. What are some numbers bigger than 0? 1. And I could keep going. 2, 3, 4, 5, 6 if I wanted to. What are some numbers smaller than -1/4? -1. Again, -1/4 would be here. -1 would be here. Notice that 0 is closer than -1. That's why this graph is going to be kind of weird and off-centered. We have -2 here. My graph, though, I will repeat again, will still have that symmetric value to it. So then what we do is the same thing we did on the last one. We are just plugging in a table of values. I told you I'm not going to go through huge detail on this, but I will show you that you type it in just like this. Notice that I put parentheses around the -2 when I plug it in. I put parentheses around the -1 when I plug it in. I put parentheses around, yes, even the -1/4. That ain't real pretty when I plug it in. And then I just go through and I do the math and get my answers for y. Just real quick, I'm going to show you what these answers are here. I'm not going to, again, belabor the point of a table of values. You should know how to do by now. -2 squared is 4, so 4 times -2 is -8. -8 plus 2 here is -6. -6 plus 2 is -4. -1 squared is positive 1 times -2. So that's -2 plus 1, which is -1. -1 plus 2 is 1. I'm not going to go through and do this very slowly, even though I know it's going to just blow your mind. -1/4 squared is going to be actually positive 1/16 times -2, which is -2/16, or -1/8. -1/8 plus 1/4 is the same thing as -1/8 plus 2/8, which is actually going to be 1/8. So 1/8 plus 2 is 2 1/8. 2 1/8 is the same thing as 17/2, or 2 point. Okay, 17/8. Sorry, that was a dumb mistake there. Oh goodness. Come on, pen. You can do it. That's a 17/8 there. Either way, it's a little bit above 2. Now, I know that just was totally crazy. Just blow your mind. When I plug in 0, remember that's the y-intercept. When I plug in 0, I get 2. When I plug in 1, I'm going to end up with -3 plus 2, which is -1. Notice this one did not have my pretty little pattern in the table. That's because my vertex, the middle number, was ugly. But I plugged in some prettier numbers on the other sides. Again, you can use your calculator. Don't get in a panic and don't send me a message and say, Mr. Harrison, you went way too fast. I know. I was trying to save a little bit of time, so this video's not quite as long as some of the others, even though you know me, I'm a rambler, right? So I'm going to go here, -2, -4, -1, 1, -1/4, and 2 1/8 is really close up there. 0,2 is right there beside it. My vertex and that point are really close together right there. It's kind of hard to see. And 1, -1. Now, you have to kind of take your head and kind of stretch back just a little bit to see that this graph still has that parabola shape. Now, Mr. Harrison is drawing really bad graphs right now. But this parabola is still symmetric, even though Mr. Harrison is bad at drawing. So even though these numbers were uglier, it still has that same shape like the other one. Notice this one opens down. Notice it's kind of skinnier too, because the -2 in the front makes it open down, and the 2 itself stretches it, so it flips it upside down and stretches it. So that is how you graph something in standard form. I will warn you ahead of time if you come across something that looks like this guy. Notice there's no bx term. If we think about ax squared plus bx plus c, you're actually going to like those a lot, because when you do that -b over 2a to find x, there is no b. So my b would be 0. And so what that does is that makes the middle point be 0, which is really nice when I make my table of values and put the vertex in the middle. This is going to be 0, -1 and -2 are smaller, +1 and +2 are bigger. That's the exact same numbers we used with linear. So it's really nice actually when that middle term is not there. So that is how you deal with a standard form quadratic. Now I want to just point out something off of the writing quadratic functions that we did last time. We looked at this particular example of Natalia Lasovskaya throwing the world record shot put. One of the things we talked about was the fact that 5.5 is where she lets it go through the air, and this up here would be the vertex. Guess what? If I want to find out where that throw is halfway through the air, I can do the same thing we just did. I can find the -b over 2a, just like we just did on the problems for graphing. I'm not going to do that here just because I simply want to save a little bit of time on this particular example. But you would just take the opposite of the 0.9325 divided by 2 times this ugly -0.01347 on the bottom. And it would give you a number right here that is the x value of my vertex. If I want to find the maximum height of the ball, the shot put, I would find the y value by plugging in the x. Just like we did in the table of values, we plugged in the x for the vertex. Let me go back, sorry. Plugged in the x for the vertex to get the y. So it finds that top point, or that maximum point. Now, we are going to talk about this a little later when we try to find out where it hits the ground. It's a little tricky on this one because it doesn't start at the ground on this side, so it's not perfectly even. But we will talk about how we can find that point later using some techniques when we solve a quadratic equation. Now what we're going to look at is we are going to look at the two other forms that we have mentioned last class, the vertex form and the intercept form. Now here's the great news about vertex form. Remember last time in class what we talked about is that when you are dealing with vertex form, your vertex is basically staring you in the face. If you take the opposite of this number and the same as this number, you're going to get your vertex. Your vertex is going to be whatever h is, because it's the opposite of -h, and whatever k is, because that's the same. Your vertex for quadratics and vertex form is basically staring you in the face, which makes a problem where I want to graph that one a lot quicker than standard form. So let's look at an example of this. Let's say we have y equals, let's go 3, even though it's going to kind of stretch it out a bit. We'll move it around. We'll say x minus 2 squared minus 7. So that is what we consider vertex form. Now, vertex form for me, what I like to say is I like to say that it has that parentheses squared. That's what I'm looking for vertex form. But the key thing is if I take the opposite of this and the same as this, that would be +2, -7. That is going to be 2, -7. That's where my vertex is located. Just like over here on this example with standard form, when I found my vertex here at 1, -4, because I found my vertex. Guess what? When I have vertex form, I find my vertex immediately. Then I can now find my whole graph by doing the same techniques I did a minute ago. The only major difference is when I put this in the middle, I already have the x and the y. So I don't actually have to plug in 2. I've already got the x and the y. What are some numbers that are smaller than 2? 1 and 0. What are some numbers that are bigger than 2? 3 and 4. It's counting, guys, and I'm not trying to make anybody feel stupid. It's 0, 1, 2, 3, 4. and then I plug in, just like I did before, into this function. I plug in 0, do the math, and get the y. I plug in 1, do the math, and get the y. And now, because this is a really pretty number, these on this other side are actually going to be a repeat, because it's going to have that perfect little mirror image, because I didn't have an ugly number like we did a minute ago. So I plug in these numbers. I go to my calculator, and I say, all right, we're going to plug in 3 times 0 minus 2, and then we're going to square it, and then we're going to do minus 7. Make sure your minus 7 is not up there in the exponent, and it gives me 5. So that's my y value. Then I'm going to do the same thing, but this time I'm going to do 1 minus 2. So I come over here in my function, change that to a 1, and boom, -4. That's the beauty of Desmos, is it helps me get those points really quickly. And if you did this one, and I'll just go ahead and show you on this one, if you did the 3 and plugged in 3, you're going to get -4 again, because that's on the other side of the vertex. And remember what we said, because this vertex is a nice pretty number like 2, it's going to give me my 0, 5, then it's going to be 1, -4, 3, -4, because I already plugged in 2, -7, that's where my vertex is. And then this one is going to be 5 again, because it's going to be that mirror image whenever that middle number is nice. 4, 5. Now this one, I can go ahead and tell you, Mr. Harrison's going to struggle drawing this one, just because I get a little shaky. Oh goodness, that's even worse than I thought it was going to be. So I get a little shaky though when I have to stretch these parabolas out. I do so much better when I'm doing it on paper and pencil. It's a whole lot easier than drawing on this little screen. So with the vertex form, the only difference when you are graphing with vertex form is how you find the vertex. Now the remainder of this video, I want to focus in on the intercept form, because the intercept form is going to be one that we use quite a good bit, but it's also probably the one that requires the most work to find the vertex. But the things that it also tells us, specifically the x-intercepts of the graph, remember these graphs, when we talk about intercept form, what we mean is we're talking about these parabolas, right? This point and this point is what intercept form really helps me with. So when we are dealing with these points that we're finding, the intercepts, they're actually going to become very important for us. So I'm going to try to make just a little bit better drawing here. Let's draw one here, see if I can. Yeah, that one's a little better. So we're finding these intercepts. Use your brain a little bit here and think, if that's where the intercepts are, remember these are symmetric graphs. Think about where the vertex would be. And again, Mr. Harrison just struggling to draw on this when I'm recording it for you. I'm sorry, guys. So right here is the vertex. Think about it. Look at where that is compared to the intercepts. It's halfway between them. I hope somebody was saying that at the screen. Maybe you were, maybe you weren't. Can't hear you. No, seriously, guys, when we look at this, that's where the vertex is. The vertex is always in the middle. It's in the middle of the table when we make our table. It's in the middle of the graph when we connect the dots. So guess what? If we know where the intercepts are, the vertex is in the middle. Now, we don't know where the y value is. We just know that it's in the middle of the two x's. So how do you find the intercepts? Well, this goes back to something that we did in the linear chapter. Remember, I told you if you wanted to find the x-intercepts of a linear equation, the x-intercepts are on the x-axis. It's the points where the y value is 0. Meaning, if I want to find the x-intercepts of a graph that's a quadratic, I do the same thing. I let y equal 0, and I figure out what they are. Now, the problem is that gives us this, 0, and I've got this x minus p and x minus q. I have no clue how to do anything with that. So what we're going to do is we're going to throw in some actual numbers here for our first example, and I'm going to show you how you actually find what those intercepts are when you plug in 0 for y. So again, to find the x-intercepts, you plug in 0 for y. That's what we did with linear. That's the same thing with quadratics. So we're going to come over here, and I'm going to write down our first example. So if you're the note taker, you may want to write this down. I'm going to use -1/2. And I'm going to say x minus 4 and x plus 6. So if I want to find the intercepts, that means, like we talked about before, the x-intercepts are going to be when I plug in 0 for y. Now if you're looking at it, you're just thinking, oh, Mr. Harrison, that still didn't help me when you put numbers in there. They still look like a bunch of variables just because there's still variables everywhere. So what we're going to talk about is a concept that's actually going to help us when we're solving equations as well. What we have here is we have what's -1/2 times x minus 4 times x plus 6, and it's equal to 0. Now, I usually have a few people in class when they see this intercept form for the first time, they ask me, like we talked about in the previous video, can we just multiply that together and just get it in standard form? Absolutely, you can. The problem is it's going to be less efficient for you because I'm going to show you something that we're going to use not just for graphing. And it's going to be something that's important. Those intercepts are key because those intercepts are when the function equals 0. Like I said, the y value is 0. And that's going to be important because we're going to use that to help us when we solve equations. So here's what you need to know. There's a special property. When you multiply -1/2 times x minus 4 times x plus 6, when you multiply this times this times this, you get 0. Well, Mr. Harrison, that's because you put 0 there. Yes, but it's still equal to 0. So I'm going to ask you a question. I want you to think about it in your head. If I told you that I'm thinking of 3 numbers, and when I multiply those numbers together, I'm not going to use the little multiplication symbol, we'll use parentheses. If I multiply those 3 numbers together, A, B, and C, we'll call them, and I get 0, what do you know about one of these numbers? If I just thought in my head, I said, guys, I'm thinking of 2 numbers, and when I multiply those numbers, I get 0. Everybody in this class would probably say, oh, that means one of them's 0. Because when you multiply things together, the only way you get 0 is if one of the numbers is 0. That is called the zero product property. It says let A and B be real numbers or algebraic expressions. If A times B equals nothing, then A equals nothing or B equals nothing. There's no other way around it, guys. If you multiply something together and it gives you nothing, one of those things has to be 0. So look back up here. -1/2 is definitely not 0. It's -1/2. But x minus 4 could be 0. X plus 6 could be 0. Notice what I just did. I took that ugly quadratic that was multiplied together to get equal to 0, and I used my knowledge about how things multiply together. When things multiply to give me 0, one of them has to be 0. And then I broke it down into 2 possibilities. Either, I'm going to use that word actually up here, either x minus 4 is 0 or x plus 6 is 0. And these equations right here are smaller, easier equations. And that's going to be the whole thing that we do when we solve equations later in the chapter. So when we say x minus 4 is 0, if I add 4 and add 4, that would give me x equals 4. Guys, look up here. If I plug in 4, 4 minus 4 would be 0. That means if I plug in 4, my y value would be nothing. Now let's go to the graph. What does that mean on the graph? If I plug in 4 and I get 0, that means 4, 0 is my x-intercept. Because 4 gives me nothing for y. The same thing applies to this. If x plus 6 equals 0, if I subtract 6, then x equals -6. Look up here. If I plug in -6, I get nothing. Because 0 right here times these would be nothing. So that means on this graph there are 2 places. -6, because if I take -6 here, I'm going to write this down again real quick. -6 would make y equals 0 also. That means -6 and +4 over here give me 0. And that means my graph will touch the x-axis at 4 and -6. Now some of you are probably kind of picking up on a little bit of a shortcut here. Let me warn you that if you're looking at this and saying, oh, I just look at that, it's a -4, so it's got to be 4 here. 6 here, got to be -6. That's fine. If it's just a 1x and a 1x in the parentheses. When the stuff in the parentheses gets uglier, you literally have to set it equal to 0 to find what makes it equal 0. And so that's what we're doing, guys. We're finding where it's equal to 0. Yay, Mr. Harrison, we got 2 points. We spent a lot of time on just 2. Well, these do get quicker, I promise. But here's what else we know. If I know where the intercepts are, the things that make the function equal 0, halfway between those zeros, or the x-intercepts, by the way, I should say this, that's another name for the x-intercepts, because it makes the function equal 0. Halfway between those is the vertex. This is going to give me the ability to find the maximum or the minimum value for the function. It's also going to give me the ability, just like we did over here where we found the vertex, and in the middle of the graph we made the rest of the graph with a table. Just like we did over here with standard form, when we found the middle of the table, we found the rest of the graph. Just like we did here, we found the middle of the table, that's the vertex. So in the middle of the 2 intercepts, 4 and -6, in the middle is where I'm going to find the vertex. Now this one's very similar to the standard form. We're only going to know the x value, not the y value, so be careful with that. So how do I find the x value that's in the middle of 4 and -6? There's not a little formula for this, although you can use a little formula if you know what it's doing. If I want to find halfway between 2 numbers, I take those 2 numbers, 4 and -6, I add them together and divide by 2. Like I said, it's not really a little formula that you write out any variables for. It's just knowing how to find halfway between 2 numbers. If you do that, you'll get -2 divided by 2, which is -1. That means somewhere on this line is my vertex. -1. I don't know where it's at. It's not here. Remember, it has to be the highest point or lowest point on the graph, so it's not there. It's on that line somewhere. So then I just do exactly like I did on the other ones. I plug in a table of values. Here's the good news, though. Because I did all this work to find the intercepts, these 2 points here, when I make a table of values for this one, I don't have to plug in as many points, because I got -1, I could plug in -2, and I could plug in 0. Those are the numbers that are to the left and to the right. I don't have to plug in every single number that I normally do. Here's the thing, though. If you plug in a bunch of those numbers, it's going to give you a better graph because you're going to get more points than just 3, even though technically I already have these 2 points, the intercepts. So when I plug these in, again, I'm going to try to conserve a little bit of time here, so I'm going to do a little bit of this work in my head. I know you're going to get mad at me. You can use the calculator. And I apologize for the handwriting in this tiny area. You're going to have -6 here and 4 here, which is negative 24 times a negative 1/2. That's going to be positive 12. So it's going to be actually up here, kind of above the graph, up here at 12, negative 212. Then I'm going to plug in the vertex. Negative 1 minus 4 is negative 5. Negative 1 plus 6 is positive 5, so that's negative 5 times positive 5, which is negative 25, times a negative 1/2. That's going to be a positive 12.5, or 12.5. So the vertex is just slightly above that one. And then the next point is going to be a mirror image at 0. Now you can see that this one, because those points are way up here away from the intercepts, that's because Mr. Harrison just made these numbers up just a minute ago. You should see that this graph, though, still has that parabola shape. Wow, I was doing good there for a minute. Still has the parabola shape like we did on the others. And so then when we come down here, it still has that mirror image. It would be better if I had some more points in here, but it still has the same shape. So I'm going to recap what we've done with all of these problems, and then we're going to look at just a couple small quick little ending examples. To find the vertex in the middle for a standard form, you do the opposite of b over 2 times a, the opposite of negative 2 over 2 times 1, and you put it in the middle of a table, count to find the other x's. Then just use your calculator. Connect the dots. Came over here, and I looked at vertex form. In vertex form, the opposite of this number, the same as this number, is the vertex. We put it in the middle, because it's in the middle of the graph. We pick some numbers that are smaller than 2 and bigger than 2 by counting, plug them in, get the points, and plot them and connect. The same thing applies to this intercept form. The only thing that's different is the intercepts, I have to do a little bit more work to find them because it's where the function equals 0. So I have to set it equal to 0, set it equal to 0, and those are my intercepts. Halfway between 4 and negative 6 is the vertex again. Put it in the middle of the table. Then some numbers on the other sides. So, just real quick, let's make sure we are solidifying that vertex form one more time here. Let's say we have x minus 2 times x minus 4. So if I want to find out the intercepts, again, it's where the y value is equal to 0. So that means where I find 0 for this whole thing, x minus 2 times x minus 4. I'll repeat that 0 product property again. This times this equals nothing. That means x minus 2 could be nothing, or x minus 4 could be nothing. Both of those would make the whole function equal nothing. So that means x minus 2, if I add 2, will give me 2 is one of my intercepts. Add 4 here, and I get x equals 4. 4 is my other intercept. What is halfway between 2 and 4? So if I'm thinking about the vertex again, the x value of the vertex is going to be halfway between the intercepts. So add them together and divide by 2. Well, what is 2 plus 4? That's 6. Divided by 2 is 3. Now, some of you are thinking, wait a minute, Mr. Harrison, you wasted a bunch of time because I can look at it and tell you that 3 is in the middle. Well, then do that. I'm not asking you not to use your brain. 3 is in the middle between 2 and 4. I'm just showing you how to do it mathematically in case you come across something that's a little bit uglier, like a word problem. Then we can plug in some tables here. Again, 3 is in the middle. Notice if I go down to 2 and 1, up to 4 and 5, this right here, let's get this to work here, is my intercept, 4 and 2. I don't need to plug those in because I already know those. But I do need to find the vertex and the other points, and it'll give me a nice little shape of this graph. To save some time, I'll tell you that this one's going to end up here and here, and you're going to end up with that quote unquote, I say normal looking parabola because there is no number out in front here. All right, so the last problem is, what do I do with that? What does a vertex help me with? Yesterday, or the other day in class, I should say, when we were looking at our writing quadratic equations, we came across this example for this music-oriented website where we had the revenue is equal to the price times the number that you're selling. And we figured out that 16 plus $1, but we did the beginning amount plus the move of $1, 1x. And then we said the number that you're selling right now, the beginning amount is 30,000. But if you jack the price up $1, you lose 1,000 people. So essentially this little x here, every time I jack the price up $1, I lose 1,000 people. That's what that x really stands for. It's how many times I change the price and how many people I'm going to end up losing times 1,000. This right here is intercept form. Mr. Harrison, why does that matter? Because look at what the question's asking me to find. I want to know how to maximize my annual revenue. Find the maximum revenue. Guys, that on a graph is the vertex. Yeah, so what? Look at what form it's in. You can find the intercepts, and where's the vertex? Halfway in the middle. So instead of me having to multiply all this crap out right here and put it in a standard form, all I've got to do now then is just take this, set it equal to 0, because that would be when the graph is at the x-axis. That is when it is equal to nothing. That really is not good in this case, because that would be when the revenue is nothing. I don't want revenue of nothing. I want to know where the middle of those 2 points are. But if I find these 2 points by subtracting 16 over here on this one, let me scoot down a little bit here. Add the 1,000, that'll give me 30,000 equals 1,000x. Divide by 1,000 and I get 30. That means on my graph, negative 16, which would be somewhere over here, and positive 30, those would be the two values where this graph is nothing. But in the middle is going to be where my actual vertex is. So how do I find halfway between negative 6 and 30? Negative 16, excuse me, and 30. The same way we did when we were graphing. Add them together and divide by 2. That's going to be where my vertex is located. Guys, just because we're not actually doing a detailed graph on this one, doesn't change how you find the vertex. So we add negative 16 plus 30 and get 14 divided by 2, which is 7. That means 7 is the number for x. That's the trickiest part of these problems, is a lot of people get really excited because they found the vertex. But the vertex, you actually have to plug it in up here to know that you're going to charge people $23. And you're going to lose 7,000 people down to 23,000. Now that sounds scary, but let's look at what we would have had here. Let's look at that real quick and we'll be done. So we started off at $16, right? Price times number sold, 30,000. And we talked about this last time. You got 480,000 bucks a month. Or a year, I think it's a year, sorry. If we jack the price up $7.23, now we're thinking, logically that doesn't make sense. We're going to lose 7,000 people. There's only going to be 23,000 people now, but watch this. When there's only 23,000 people, I actually increased my price, or my amount of revenue, I should say, by $49,000, even though I lost some people. Now, there is something to be said for, you do have to think about loyalty of people. Sometimes you can get some advertising out of people. So I'm not saying you go full scale on this and jack the price up $7 immediately. But if you kind of scoot the price up a little bit, this is what you see with companies like Netflix and things like that. They kind of scoot the price up a little bit and they kind of measure it out and see the, how if people get real upset and real mad, they kind of stop and don't raise it up anymore. But they're trying to look and trying to get as much money out of this as possible. That's how business works. And you can use these intercepts and the vertex to help you actually apply these quadratics to real life.